Thank you for coming, everybody. My name is John Dunn. I am not Dr. Gan Paparisto, my colleague. He did not make the trip. He's a systems guy, and I'm an EM guy. So there you go. And my colleague, you heard a couple talks ago, Joel Kirschman. He's also a systems guy, of course. What we're going to talk about today is MIMO and beam steering modeling in support of 5G applications. Briefly review why you want to be able to do that, of course, with 5G. And then AWR, we are a software company. It's our charter, our mission to give you good software. So as part of that, we better be able to support these things if you're going to use us for 5G. And we're going to look both at the circuit level. We're going to look at the antenna design level, and we're going to look at the system level. So we actually have three different parts of the software we're going to look at. So system, antenna design, and circuit simulation. I will look at all three of them. So let's get going. I was informed that no one has taken their full 30 minutes yet. So that's over. I can go on for days and days. Part of this talk I actually gave in Japan. I was there a few months ago. We ran a marketing thing over in Japan, so I gave part of this talk. And when you go to Japan, there's three reasons they send me to Japan. One reason is I did the talk. The second reason is I'm from America, so they think, wow, these guys care. They sent someone from America. So I'm kind of an ornament. And then the third reason I've acquired the skill, I can talk extremely slowly. And so in Japan, I talk about this fast for 2 weeks. And you talk this fast for 2 weeks, and you feel like an idiot doing it. And at the end, they go, you speak English really well. We understand you. So I can make this talk really long if you want, but anyway. Okay, so let's talk about 5G. If you haven't heard of 5G, you're in the wrong conference. This 5G, to quote Muddy Waters, it can cure the sick, raise the dead, and it's going to make everybody talk out of their head. It's going to do everything. As I understand, as a matter of fact, part of this, it has specs. I can talk to my toaster. The Internet of Things, you're going to be talking to your toaster, your refrigerator, everything is talking. And as part of 5G, and many in this room probably know, from Joel's talk, I understand many in this room know these specs far better than I do. But the point is, we've got a lot of data going around and a lot of requirements for energy consumption has to be low energy, has to be high data rates, et cetera, et cetera, et cetera. So when you look at those requirements, we have some challenges here, and it quickly gets us to things like phased arrays and MIMO type antennas. You may not be aware on the 5G of deployment, 2000, I think I have it here. Yeah, initial deployment 2020. They're actually trying this thing out in a couple different spots. The Winter Olympics in Korea, 2018, they're going to be looking at 5G with all kinds of amazing stuff, including, I imagine, everyone will have things on their helmets and you can ride along with them. 360 virtual reality, lots of very high-speed data going on. So this is the Koreans in the 2018 Olympics. In the Summer Olympics in Tokyo in 2020, they're rolling out 5G. In the talk in Tokyo, I didn't mention the Koreans were going to be ahead of them on this, but it's true. So here you have, this is Tokyo. They're already trying things out. And this is actually the neighborhood I stayed in. It's in Yokohama, south part of Tokyo. And they actually have an array up there, these towers on these arrays, and then they have these various vehicles and things, and they're checking this thing all out already. And you need a lot of phased arrays. It's definitely MIMO. One of the Again, in Tokyo, one of the embarrassing things for the Japanese about this slide is guess what company was doing that? It's called Huawei. And so I didn't mention that either. Anyway. Okay, so let's get to some substance here. So I'm not going to go through this slide in amazing detail. You people are very aware that 5G is going to, if we're going to carry these kinds of data rates and efficiencies, we need to do a lot of stuff. So first of all, the physics of it, you're going to need higher frequencies, and you can see them there. This is going to present a lot of challenges to designers. Let me give you one example of that with cell phones, actually, you may not be aware of. If you take cell phones nowadays, working at a couple gigahertz, when they build these phones, for the designers, one of the big revolutions in that technology has been BAW SAW filters. And that has allowed them, for example, with LTE, where you have, 32 bands. I mean, you have this amazing number of bands. They can get tremendous filter performance relatively cheaply with that technology. If you're not familiar with what a BAW filter is, it's bulk acoustic wave filter. It uses acoustic technology, and it's really been a revolution in these phones and this filtering. It's kind of wiped out everything else. Well, guess what happens at 28 gigahertz? They don't work. So that technology is going away, or it's going to have to be, it is not a known problem, it's an open problem. It's what we dismissively call at our company a science project. That's when the manager comes in, they go, that's a science project, meaning they don't know how to do it, okay? So they're going to have to be using different technologies here for those kinds of bandwidths if you're a hardware engineer. We're not going to just turn the crank one more time. So there's a big challenge. Efficient power schemes, power is king, saving power, especially with mobile devices, okay? And as part of that, of course, with the antennas, et cetera, people are looking at much more distributed systems with smaller cells. And finally, we do get to antennas, a critical part of 5G, if we're going to get that data around. And we're going to be looking at massive input and output schemes with very tight beams and integrated phased arrays. So physically there with the integrated phased array, think of the array with the module and the amplifiers. I gave a talk earlier today which kind of focused on that. All right, and then finally, if you heard Joel's talk, of course, with system integration, again, when we build the system, we're going to be relying a lot more on module technology, which we're working on. You want everything in one module. It's cheaper, it's more compact, and a lot of integrated components. I had mentioned that BAW SAW problem. So for example, one of the technologies they're looking at is actually passives. So think inductors, think coiled wire embedded in glass. So you're going to have a glass substrate in your module with literally inductors and capacitors embedded in it. One of the advantages of 28 gigahertz is things are smaller. So that's what you do. You can now all of a sudden start doing, quite frankly, a wire, you know, a loop of wire at 28 gigahertz starts making sense because it's small enough. So they're actually, you're going to start seeing all this sort of stuff. Okay, we're going to need great antennas, and there's a little effort on the left there with MIMO, massive input, output. Energy, it's much more efficient energy capacity. So we in the software industry have to be able to support that, and that's what this talk is about. Okay? I like the bug on the right. It has nothing to do with the talk. But okay. I was informed yesterday, we say antennas. The only time in the English language you use the plural as antennae is with insects. So on the right, he has antennae, and we do antennas. How about that? There you go. So anyway. Okay. Massive MIMO, I got this out of one of the IEEE communications magazine, IEEE. I'm not going to go through the details of the slides, kind of an eye test. The point being that what it does is it has tremendous reduction in power consumption when we array this stuff, and we get tremendous improvement in capacity. Okay, that's why we're doing it. Okay, now if you did go to Joel's talk, the talk before this one, he briefly mentioned, his was all about systems, he mainly focused on 5G standards. He briefly mentioned things like the phased arrays in VSS, or system simulator. I want to go into that in a little bit more detail and show you some of the features of that, because I think he just had one slide and he went through it pretty quickly. Phased arrays are important. System simulation is important if you're going to do 5G. How do you account for the phased array in the system simulator now? Not the circuit simulator, the system simulator. And we've been struggling with that, and we actually now have an element, and it's that little guy right there, the TX phased array, transmitted phased array element. Inside that element, there's a whole lot of stuff going on. And that arrow and that other diagram kind of shows you what that's equivalent to. What you're seeing there are multiple channels, each with their own elements, phase shifters, amplifiers, et cetera. And they're actually all hidden in that phased array element. And we have then a channel, we have a receiving antenna. Here you see an expansion of one of the channels, and which would be going to one of the elements in your phased array, and you can see filtering, amplification, et cetera. So that is all in that phased array element, and I'll show you here in a couple slides some of the other cool stuff that it does. The big picture being we are actually modeling the phased array in the system simulator now. So when you do your channel modeling, et cetera, you can include it. And that basically shows you the model. Okay. So the point being there is you can enter what goes into this in a variety of ways. Most people would actually, you could write, there's a little table you could make. It's an ASCII file, and we actually even have something that generates it so you don't have to do it yourself. Let's get to the fun stuff. What can we do? Okay, so we have a phased array element. And what that does is we have the standard channel elements for the system. So you'd have an amplifier model, system amplifier model, et cetera. Well, how do you model the phased array? Well, what we're doing for the actual array is we are just using the standard antenna array equation that many of you know and love. Essentially, it's n sine theta over sine n theta, where n's the number of elements. But then we spiff it up. So what we do, for example, is you can actually put in the real patterns, antenna pattern, of each given element. Now, I appreciate when you have all the elements together, the pattern can change. But if you think of standard antenna theory, the standard thing to do is to multiply the antenna equation by the pattern of one element, which gives you the total pattern. That does ignore coupling between the elements, and so things like scan blindness you can miss. But at the system level, we argue it's a pretty good first step. Later on, I'll show you we actually can look at coupling between elements, so we can do better, start to look at some of those issues. But right here, what we're doing is the pattern for one element multiplied by the antenna equation gives us the array pattern. And the nice thing is that pattern you can get from an EM simulator and then put into the system simulator. So don't think it's an idealized dipole. If you had horn antennas, you could actually have the actual pattern in there. So that's kind of neat. We're going to come back to that element, but I want to show you some of the other things in the software quickly. We're stepping away from system simulation here. This guy is actually a tool we have called Anson. This is a new product for us. What it is it synthesizes antennas. It's an antenna synthesis tool. And as part of that, we actually have array elements in here, so you could synthesize an array. What you do in this tool is you actually put the specifications you want in the tool. You can specify the type of array. I want rectangular patches, or what's really neat is you can actually let the tool decide what type of antennas. And you can actually, believe it or not, it can say, I want a patch, and it might go, no, you really want an inverted F. You're going to do better with an inverted F. So it's kind of neat. What you're seeing in this diagram here on the left is they're putting in the constraints for the optimization, and you can see the pattern. The lobes have to be at a certain level, the VisWAR, input impedance, the standard antenna things you'd worry about, and then it's going to select from those elements in this example. And again, we could even array that. So it's kind of a neat product. And here's the results here. This is a simple single patch, and again, you could have an array of these, and it's met the specs for those dimensions. Well, I'm jumping around a little bit. We're back at the system simulator. If I go back a couple slides, I remind you, we had the pattern, excuse me, that we could put in. Here's an antenna array. Another thing we can do in that system level model is we can include some coupling between elements. This is an improvement. There are things out there like scan blindness and degradation of your pattern, which is only going to be apparent if you include coupling between the elements. And in the system level model with this array example, we actually, the engineer has set up 3 different zones. There's a center zone where an element would couple to its neighbors. You would get that from EM simulation. We have an edge where an element would couple to just its neighbors, and of course you'd have the edge. And then we have corners. So you actually, in EM, if you do a couple simplified things with a patch and a couple neighbors, you can then include those patterns in the array at the system level. Okay, the system model, I'll go quickly through this. It supports a number of different architectures. Besides the classic Cartesian XY type of lattice, you can do circular, you can do irregular, pseudo-random if you want, all right? And as part of that, you can start removing elements. So the system designer now, you've got your channel, and you're sending through your 5G signal, and we can do that all in the system simulator. You start removing elements, you're going to degrade the pattern, and you can see how badly it degrades before you're in trouble. And so you can actually look at things like element failure, which is going to happen in the real world, and you can stay in the system simulator on that. Okay. We're still in the system simulator here, VSS. Massive input, massive output, and again with the antenna element, we can actually start looking at, we can start sweeping the beam. So what we of course do is we adjust the phase and amplitude of, of each channel going into each element. You can do that relatively easily. And you can start steering the beam, and what you're seeing here in the right picture is the result of that. And so you're actually getting various, the beam steering. Here's a multi-beam example. Joel mentioned this in his talk. So as a 5G engineer, designer, system designer, you are worried about, you have 4 different LTE signals. They're at different beam angles. And as those signals interfere in the side lobes, et cetera, or you start getting the main beams close to each other, you're going to get a degradation in the signal. And Joel mentioned this. And you're seeing the beams in the antenna diagram there, the pattern. And then on the right, you're seeing the information getting through. And the point being, as the beams get closer, it degrades. Because what happens is the beam signals are interfering. So we actually can do all of this in the system simulator. Here's a more complicated example, 28 gigahertz proposed for 5G. This would be a transceiver phased array, again using that element. I'm not quite sure how many elements are in this array. I would guess eight element array, but I'm not sure. And they're studying various things here. I believe, again, I pull up my glasses, I'm not going to be able to read it. I believe the one on the left is we're varying the gain of the transmitting array. The one in the middle, I think we're varying the power going into the array. And the one on the right, they're varying the frequency. So, of course, as you scan frequency within your channel, I mean, does it make a difference? And you can see there's a slight difference there. All things that the system engineer would be worried about in this type of situation. Okay, I'm going to leave the world of system simulation for the last part of the talk here. I think, what do I have, 5 minutes? 5 minutes? 7. I better slow down. Yeah, I can just keep going. It's amazing. Okay. We're going to the circuit world. Okay, we've been in the system world, and so a lot of system stuff. Get the phased arrays in the system to model the channels. We've been at the antenna level. I showed you the little tool where you can actually make your own antenna. You can synthesize it. You can make arrays. And I'd like to do the last part of the talk. I'd like to talk more about the circuit world. Now, phased arrays in the circuit world, what do we care about there? Well, you know, there's the obvious stuff like the electromagnetic simulator. You want to obviously simulate the phased array to get the S parameters. But unless, some of you may not have thought of this issue, which designers have to deal with. Now, these would be people actually making the circuitry. In these phased arrays, the transmit array, you're driving it with power amplifiers. And so typically in these modules, there are different schemes, but one of the more common ones would be you'd actually put a power amp behind every one of those elements, okay? And in the world of miniaturization, et cetera, you can do this, of course, with chip technology. So imagine an integrated array with a power amp chip behind each one of those guys. Okay, fine, we have power amps. Power amps are highly nonlinear amplifiers. They're typically class E, class F, et cetera. And when you have a highly nonlinear amplifier, it depends heavily on the load it's driving. As you change that load, you change the characteristics of the power amp, and you can degrade its performance. And those of you in this game, this is why you spend a lot of money and time doing something called load pull. If you're not familiar with that term, what they do is in a fancy machine, they're actually changing the load that the power amplifier is driving, and then they can see the performance of the amplifier, and they're designing to that. Okay, well, these power amps are driving a phased array. And the point is, as you scan the array, what happens to the input impedance to the elements? Well, guess what? It changes. And so as you scan the array, the load impedance that the power amps are seeing is changing at each one of those elements. And what can happen to you, you scan the array and you actually get lousy performance as you scan because you didn't account for the degradation of the power amplifier performance. Traditionally, to handle this, it's a real pain because what you have to do is you get the S parameters from the EM, and then you actually just have to idealize sources to figure out the load impedances. And then you run over to the circuit simulation, put those in, and then you run harmonic balance to figure out the power. You run back to the array, input the power, you look at the pattern, you read off the power, you know, you have to go back and forth. And one of the neat little features we put into the software to help you with the phased array as a circuit designer is it actually talks to the circuit now. So what you can do is you scan the thing. Actually, I don't have I thought I maybe had a blow up of that one on the lower right. And what you're seeing is the circuit, and there's 16 elements there driving each one of the elements of the phased array, the S parameter file we got from EM. And so what you do is as you're scanning the beam by changing the tuning of the tuners in the circuit, it automatically couples in the S parameters, reruns the harmonic balance with the new load, and it's all done automatically for you. So It's kind of neat, saves a lot of time, and it's something if you're dealing with phased arrays for 5G, you're just going to have to deal with. You're going to be working with highly nonlinear amplifiers in a scanned array environment. Okay, well, I'd like to conclude. So, okay, the first one says our software is great, yay, all right. I'm in marketing, so it's true. We always tell the truth. No, it is. Stop by the booth if you want, more details. We're big fat NI booth. I think we're right in the middle of the room. You can't miss us. I think we're the biggest booth at the conference. But besides we make great software, the point being 5G is going to have phased arrays. It's got to have phased arrays. It's going to be beams. If you're a system engineer, you are going to want to include those in your channels. Somehow your system software has to have a capability of doing so. I showed you ours, has some nice features. Second of all, if you're an antenna designer, obviously you need EM simulators we haven't talked about. I did show you kind of a neat tool, antenna synthesis tool to help you out. And then third of all, if you're a circuit designer, phased arrays, you're driving those things with your power amps, which are highly nonlinear. They are coupled together, and you have to have an environment where you can easily handle that. So I just wanted to give you an overview in this talk of some of the things we're trying to do to help you in your jobs as you deal with these MIMO problems in support of 5G. So thank you very much, everyone. Have a great show.